Although there are billions of stars in the cosmos, the one at the center of our solar system has a specific function for those of us who live here on Earth. The Sun's fiery core, strong gravitational pull, and vast magnetic field all contributed to it being the heart of the solar system. Hello everyone, I am Rica ALFORQUE, and now let's talk about the part of the Sun. By the end of this video, you should be able to identify the inner layers and the outer layers of the Sun. Furthermore, you should be able to differentiate the different parts or features of the Sun. The Sun is divided into 6 layers. We will tackle them one by one in the next slide. First, let's talk about the inner layers or the interiors of the Sun, which compose of the core, the radiative zone, and the convection zone. Deep inside the Sun is the innermost layer, the core, which is a gigantic nuclear factory that extends up to 25% of the Sun's radius. The temperature in the core is at least 15 million Kelvin or 27 million degrees Fahrenheit. And under those conditions, the hydrogen is completely ionized, which means the electrons are stripped off from their protons. As a result, the core becomes a thick soup of extremely hot subatomic particles. In fact, the protons are squeezed so hard that an amazing thing happens. They fuse together to form a heavier element called helium. And some nuclear energy held within those atoms is released along the process. This is what we call nuclear fusion, and it's the very process that keeps the Sun and all the stars alive. Above the core is the radiative zone, extending outside of the Sun's core up to 70% of the Sun's radius. In the image, it is the part where you can see the arrows. Radiative zone is the site where energy transport occurs. This energy is carried by the photons in the process called thermal radiation. This zone can be characterized as the place where the photons bounce around, facilitating the ability for energy to be transported to the outer surface of the Sun. The temperature at the radiative zone ranges from 2 to 7 million Kelvin. Above the radiative zone is the convection zone. Convection zone begins at around 70% of the Sun's radius, and at this point, the density is finally low enough for light leaving the core to turn into heat, and the process called convection begins. In this zone, the heat is transferred by thermal convection through thermal columns. Convection, to express simply, is the phenomenon whereby hotter material rise while colder one sinks. Now let's proceed to the outer layers of the Sun, which is composed of the photosphere, the chromosphere, and the corona. A visible bright yellow surface of the Sun is called photosphere, which is the Greek for light sphere. Because it is where the visible light first appears, it is the layer of the Sun that we are all familiar with, the only part of the Sun that we can see from a typical day without the use of any specialized equipment. The photosphere have 2 important properties. First is the sharpness of its edge or its limb. The sharp edge of the solar disk shows that the density decreases rapidly in the Sun's outer layer. Second is the limb darkening. Limb darkening is when we look into the Sun, we would see the center is much more brighter than its edge or than its limb. That shows that the temperature decreases outward in the visible layers of the Sun. So when we look into the edge, we see the higher and cooler part of the photosphere, which is darker. And when we look into the center, we see the lower and hotter gas in the photosphere, so the center appears relatively bright. When we look closer into the photosphere, we would see that it is covered in a granular-like pattern that is a result of wild convection processes that is happening in the convection zone. We can see the top of the thermal column in the photosphere. The bright region is called granules, which are rising columns of hot gases, and the irregular lanes in between them are places where cool gas is descending into the interior. Sunspot is the dark spot on the sun formed when an intense magnetic activity in the convective zone ruptures a thermal column. It is dark because it is much more colder than its surrounding. The inner darkest spot of a sunspot is called the umbra, and surrounding the umbra is called the penumbra. Around the edges of the sunspot, the magnetic field lines are concentrated. This can energize the plasma even further and then heating it up, which results in a bright rim that surrounds a sunspot called faculae, which is Latin for little torch. A layer above the photosphere is the chromosphere, which means color sphere in Greek. The layer gets its name because at this layer, the temperature rapidly lowers down to 36,000 degrees Fahrenheit, causing hydrogen atoms to start radiating in a reddish hue. The chromosphere and the corona, however, can only be seen in specialized, expensive equipment, but occasionally we can also get a rare peek at both of these layers from Earth during a solar eclipse. Spicule is a jet of dense gas that is released from the chromosphere of the Sun. Spicule occurs at the edges of the chromospheric network where magnetic fields are stronger, and within 10 to 15 minutes, they disperse or collapse. Plasma on the Sun's surface can also flow along the magnetic lines. This phenomenon can create a huge arc of material called filaments or prominence, stretching for hundreds of thousands of kilometers across the Sun, looking like fiery arches. Solar prominence are bright loops of solar matter, which are cooler than the corona, and they appear as darker strands against the Sun. A solar flare is brief but bright eruption of hot gas in the chromosphere. It is an intense burst of radiation that comes from the release of magnetic field linked with the sunspot. Flares are essentially giant bursts of X-ray and energy that travels at the speed of light all directions in the solar system. They are often seen as flashes of light on the sun. The flare releases photons at almost every wavelength of the spectrum. Remember that coronal mass ejection or CMEs and solar flare are both explosions that occur in the sun. Sometimes they occur together, but they are not the same. CMEs are giant clouds of particles that the sun hurled out into the space, while flares are flashes of lights occurring in various wavelengths on the sun. Corona, which is Latin for crown, refers to the sun's outermost layer. Surprisingly, this outer layer, which reaches temperature of about 2 million degrees Fahrenheit, is one of the hottest layers. The sun's magnetic field lines traps hot plasma in the form of spike line shape called streamers. These are what gives this layer a crown-like appearance. That's why its name is corona. Large plasma and magnetic field eruptions from the sun's corona are called coronal mass ejections. They develop when tangled magnetic field lines explode and release energy. They have an embedded magnetic field frozen in flux that is more powerful than the interplanetary magnetic field of the background solar wind, and they can release billions of tons of coronal material. Corona loops are ropey, curving strands of plasma that appear as arc above the sun's surface. Hot, dense plasma causes these loops to glow. The electrified plasma flows along the curving lines of powerful magnetic fields, giving corona loops its characteristic shape. Corona loops often appear to arc between pair of sunspots with opposite magnetic poles. Thus, coronal loops are more common around solar maximum when the sun is most active and there are many sunspots. On the other hand, during solar minimum, when the sun is least active, another feature of the corona is apparent: dark patches called coronal holes. Coronal holes are opening in the sun's magnetic field where a stream of high-speed solar wind rush out of the solar atmosphere. This coronal hole appear as a dark area in the solar corona. They appear dark because they are cooler and less dense than the surrounding plasma, and these are regions of open, unipolar magnetic field. Most of the sun's energy is emitted in the form of visible light, but the sun also emits energy that cannot be seen. This invisible energy is known as the solar wind, and it extends throughout our entire solar system and even beyond. The solar wind is continuously flowing from the sun. It is made up of ionized plasma and particles that escape from the sun's corona. In this outer atmosphere, temperatures are so high that plasma expands to the point that it breaks free from the solar gravity and is released. When the solar wind leaves the corona, it carries with it part of the sun's magnetic field. This magnetic field within the solar wind interacts with planets as it flows past them. Charged solar wind particles that enters the Earth's atmosphere near the poles react with the gases within our atmosphere to create auroras, which are beautiful display of light in the sky. That's it for my topic. Thank you for listening.